Okay, so we'll get started. So this is module 4, and so far we cover quite a bit of things, right? So we covered how to work with the data using pandas. We started with that, and then so basically we know how to deal with the data, right? So then we discussed how to visualize the data, and then we spent a lot of time on that. So that's foundations, right? Like how you would analyze the data and visualize the data. Those are foundation of the analysis. However, I would say that's not enough, right? To be considered a good data scientist, you need also to know how to ensure you organize your project in a way that you can share with others and collaborate with others. And that's very, this is very essential. And I consider that's extremely important because I think science becomes like it's more and more, I think science become a team science, right? When many people work on the same project, and there are multiple reasons for that. And typically, especially in our domain, things are very interdisciplinary, right? They span a variety of disciplines. So it's very likely that people are working with other, scientists are working or students are working with other students who has who complement the expertise. Like somebody is strong in life science or in medicine, let's say, but another person is strong in computer science, but less so in life science. So they actually benefit each other, work in the team, but to work effectively together, you need to share your work effectively and so others can understand. And I think when you organize when you write your code, that same kind of comes there, like making the comments in your code and organizing that so that others understand. That's very essential. But also when you organize the results, like when you organize the notebooks, figures, and so on. So there are multiple reasons to do it kind of properly. So reason number 1, to be able to collaborate with others. For example, you do one part of the work, and then you want others to join. So if you don't organize nicely, you will spend quite a bit of time to explaining what did you do. But if things are organized more or less okay, like people will be able to understand. So that's the reason number 1. Another reason, I think, for yourself, for your future self, I would say. It's very typical in science and with the publication, things like that, like you work actively on something for months, you deliver the project, right? Anyhow, you deliver that as the report, let's say, or as the publication, or anyhow else. And then you don't actively work on the project for a while. And let's say with the publication, actually you get, let's say in 3 months, you will get the revisions back, right? The reviewers will read your paper or the report and say, okay, those are our suggestions. Meaning that sometimes you need to change something in the analysis. So if you didn't spend time or invested time to organize your analysis, then it will be tough. It will be tough for you to understand what you did, because as time goes, obviously it's hard to remember. So that happened actually to me multiple times. So I learned on my own mistakes. And then it was like, like I was not happy with myself, like past self, of organizing the data, and spent an enormous amount of time trying to remember what I did, what threshold did I use, like what parameters. I couldn't remember anything. So after that, I decided strongly, like all the time, try to invest time and organize things so that it's very easy for me, future me, to kind of like adjust them, change, and so on. So by investing time now, like you will save a lot of your time in the future. And then, like if somebody asks you to alter some parameters, like to change some parameters, it's kind of like trivial if things are very nicely organized. And actually Jupyter notebooks already, like the Google Colab, gives you that opportunity already. So I would say you're already on a good path. Okay, and then, so that's about yourself, right? And others in your group, but how about the rest of the world, right? So I think that there is a big trend right now to make everything we do reproducible, right? And probably heard many times about reproducibility crisis in science and things like that. So I would say when you do wet lab work, like experiment, that's extremely hard to document what you do, like how much liquid you add, like how you mix, for how long, and so on. That's all subjective, because you're writing that by words. You say, okay, I did this, but it's very hard to determine what is necessary level of detail so that others can reproduce your experiment. I think it's an open question. And that's why I think many reports say that this fraction, kind of outstanding fraction of the science we do, is non-reproducible. But it's unclear why it's non-reproducible, right? Is it the bias people do? Do they intentionally kind of skip some details, for example? That's one possibility. Or maybe the wet lab settings are so different across laboratories, across countries, so that making it almost impossible. So we'll not talk much about experimental science, right? We're here for data science. So I think in data science, that's more or less straightforward. I would argue, and I would make a claim, that in data science, everything can be 100% reproducible as soon as you do it right. So what do I mean by doing it right? So if you share your data you have used, let's say you want to reproduce a box plot. So what is required to reproduce the box plot? It's required to share the data points, I guess, in some format like CSV format, and the code which was used to produce the box plot. I would say that's it, right? So that's quite straightforward. Sure, if you have big analysis, you need to organize it and so on. But I would again claim that we can achieve reproducibility and transparency in data science, at least. Not talking about, I'm not touching on experimental science. I think that's less clear. Okay, so I think that's the kind of 3 reasons you have. It depends on you what you consider the most important reasons. I think to me, all of them are more or less equally important. I'm doing better science for myself, but probably better science for the community or the rest of the world. Okay, but also there are some, I think we touched base on that. There are requirements from the journals saying that, you cannot skip this. You should really share code and the data behind your results. And then I think there is a kind of more or less acceptance in the field that I think Jupyter Notebook, that's a great idea how you would share and organize your results. There is also R. I think we will touch base on that. So there is R Markdown. There is different ways you can organize your R code. We'll talk less about that. We will talk more about exploratory analysis with R, but we'll focus on Jupyter Notebooks and in this case Google Colab of how we organize and share the results. Okay, so that's kind of motivation. Oops. Okay, so another thing is version controls, right? So, which I didn't said. So version control is basically, put it simply, when you're working on the paper on the report, you say version. You probably are saving copies, saying V1, version 1, version 2, and so on, hundreds or as many iterations you did, right? And then you say final, perhaps you say final 2, and so on. Okay, so I'm admitting one more of that. So what is version control? So version control is basically, right, when you're creating versions. So, and then the idea is that not everybody is ideal and not everybody makes mistakes, right? So how we make sure the mistakes will not impact your results and analysis, meaning that sometimes, you want to explore something in your data analysis, so you kind of go one direction, but then you realize that it was a wrong direction. So you want to go 3 iterations back, right? 3 versions back. How you do that effectively? So version control kind of lets you travel in time in this sense. You went this direction, say, okay, that's wrong. Let me go back and explore a different direction, right? So it gives you a lot of flexibility, but saves every single version. So I'm not sure if anybody using Google Doc, for example, Google Doc is a good way to write because, you don't need to save intermediate results. Like in Microsoft Word, you would need to say version 1 again, version 2.
If you connect it to OneDrive, it saves you and it gives you versions of it.
Okay, excellent. Yeah, thanks, Darian. So yeah, that's a great point. So I was not using Microsoft for a while. So yeah, so exactly, so because the open question is if you do it manually, how often do you need to do it? Every 1 hour, every month, every day? It's unclear, right? But basically, automatically versions are saved. I'm glad to hear by Microsoft as well as Google Doc. Frequently, probably as many times as necessary, so you can travel back in time and say, okay, actually I want to get the version 3 days back because I remember I did this analysis, but I no longer want to go that direction, I want to go different one, and so on. So that's useful for yourself, extremely useful, and kind of, I would say, remove the stress, right, of losing the part of the analysis, being confused, is it this really the final, that is the final, just doing a proper job and setting up the system so that version control is happening, then you can always go back, right, and restore any version you would like to restore. Okay, so for that we'll be using version control and public repository. So we'll learn how to share the code publicly, right, and then that's usually a good idea to provide that as you publish your report or the paper, right? You say all the analysis and the code and the data can be found here, and you give a link, and people can access and look at your code and the figures and the results and so on. Okay, so for that we'll be using Git. We'll discuss that in a second. We'll learn how to create a new repository. So basically, repository is how to put simply, like a place online where you can store, like a folder. Okay, let's put it simple. A folder online where you can put the code and the data right there, like very simply put, and then like you can store notebooks and so on. And there is some nice functionality to enable version control, right? There is a version control in that directory. You can pull updates, like you can get any updated version of your analysis at any time, and push your changes, right? So you will be basically doing pull and push, right? Like getting the updates and pushing your new version online, right? So this is how you will be working. And we will learn how you ultimately need to share the results of your analysis by doing easy to navigate repository, right? How to create the structure, and then with the analysis which accompanies your paper or your report or anything you do. Okay, so that's kind of learning objectives for today and tomorrow. So outline, we'll start with the Git and the GitHub. Then we'll open the account on the GitHub. We'll learn just essentials. We'll not go much. We'll learn the commands. You can basically do things, but Git is the whole world. There is so much of it. But I'm pretty sure I'm pretty positive you can survive and be effective with quite few commands. And then we'll learn how to interact with the GitHub via Google Club. It's a little bit tricky because Google Club is online, GitHub is online, so it's a little bit tricky, but we'll get there. GitHub organization, how to organize your results, how to write a Readme file. I think that's essential, that's important, that's a must to do. And then we'll talk a little bit about the sharing of extremely large files. So in case you have extremely large file, for example, you run sequencing, right? And the question how you share that, or you simulated the data which is large, which cannot fit on the GitHub, because actually GitHub will not, there is some limitation in terms of space. So you cannot upload very large file on the GitHub. All right, so why do we want to use GitHub? So GitHub, it's kind of like a repository hosting service. So it's like the whole full product for you. So actually it was independent for a while. And then I think it was 2 years ago, maybe like 1 year ago, bought by Microsoft, right? So, but it's free to use, and it's quite nice. I think then primarily for your purposes, actually people using that a lot to share the code, right? They develop some software, for example, or some pipeline. So they would share it on the GitHub so others can use it, right? That's primary, I think, goal. But also it's quite nice to share the results or the results of your analysis, all right? It's per se not for others to use it, even though it's possible. They can use it and adjust it for their own data, but more so kind of to enforce and to ensure reproducibility. At least this is how we're going to use it. Okay, I think it's widely adopted at the academia community in general, and then it's a good taste, right? So I would say, like if I hear somebody doing proper documentation on the GitHub, like let's say I'm reviewing the paper, and I see GitHub link provided and things are great there, I think it gives a great impression. It gives like a lot of extra point to that paper because I feel like they're doing reproducible science. So that's something. And then if it's not the case, personally, I always require that if I'm reviewing the paper, I'm requiring that to happen, not necessarily GitHub, but something, right? So that's my strong kind of opinion on this. And the thing is, like, what is important, you will have URL, right? You will have a link where everything will be there. So it's very easy to share. You talk to somebody about your analysis or you collaborate, you just send the link and say, hey, everything is there, right? So it's convenient. And then again, that's Also, you don't need to store things on your laptop, let's say, right? You change the laptop or things are deleted, like it's permanent, more or less. I mean, if we assume Microsoft will keep sponsoring that, or they will not run out of money, but that's an open question about what is called archival stability, right? Like from internet, things can disappear, but that's an open question how we ensure that. There is some initiatives, I think, I keep forgetting Zenoda, I think, right? Or Zotero, I keep forgetting them. So one of them, which are kind of like committed to save information on the web, but that's a kind of an open question. But more or less here, you can assume that it will be forever, like on the web. So, like your analysis is saved, so you don't need to worry about that. And then what is nice for you, it uses version control, basically the process of keeping track of file changes, right? This is to put it even simpler. Okay, so that's why we need the GitHub, or like at least motivation to use the GitHub. So GitHub will store the repository. So repository is the folder with the code and the data nicely organized, or hopefully nicely organized, right? In the cloud, right? Like on the web. So that's like where GitHub is located. If you click here, you will go to GitHub. Our lab, my lab, has the GitHub where every project is there. So like I ask students and the postdocs and others, like to create the repositories for the software they develop, but as well as the analysis they do. So everything is there. It's also quite convenient for me personally as the person managing the projects, right, to see what is going on in the lab because everything is there. So, okay, so fundamentally, right, so you might have many computers also, right? Let's say you work at your university or at work, like you're doing from one kind of computer, but then you come home and you work from the laptop, let's say, right? So if that's the case, GitHub is also can nicely handle that, right? So you might have working copy on your laptop here on the user A, meaning that's your local directory of files where you make changes. Oops. And typically, like I would say, you're not sharing those changes publicly until you're kind of more or less happy with them in some sense. So you kind of you're playing locally for a while, but you say, okay, I achieved certain milestone. So I would share that, and you push the changes to the GitHub, meaning that you make your local copy of your project and the copy on the cloud to be the same, right? You synchronize them. So, and actually, if you're concerned to make them public, I think GitHub lets you do some number of private repositories. I hope it's
no private. It's free.
It's not free, right?
It's free. It's free. Microsoft bought it, and it's free.
I see. Okay, great. So it's free, right? So that's great. So if you want to do private, if you're concerned to share the data, so you can do private, so only you can see it, right? But then as you're ready, I guess, right, as you publish your report or like you're ready to share, you can like change it and make it public. Okay, so, and then let's say you have worked here during the day as the user A, and you work, and then you synchronize, you push all the changes on the GitHub. So now the two versions are the same. Now you came back home as the user B, and then what you do Git Pull, because this version is behind, let's say, right, on the user B. So you synchronize by pulling everything from the GitHub on the user B, and then it's the same. So basically user A, user B, and the GitHub are all the same. You make the changes, right? And as soon as you're done, you push them, right, to the GitHub. Now the user A is behind. So when you come to work, you Git pull, you get the changes and you synchronize again, and so on, right? So that gives you a lot of flexibility depending where you work, like you can use, and then will not touch kind of explicitly about how to work in the team, but it's more or less quite the same. I mean, because it would require much more material, which we don't have time for. So we keep it simple. We assume, I think, I will double check, but I think pretty much sure we assume that you're working by yourself on the GitHub. But if you work like as the team, there are kind of few things you would consider like conflicts and so on. So that's something, like if you need, I hope, I mean, we can discuss like later when OTAs can discuss like separately with you if you need that. But again, we were just giving you the basis, to understand. But I'm pretty sure having this basis, you can self-learn or seek help with TAs. Okay. So what is version control? Again, so it refers to a system that records changes to files or set of files over what we call versions, right? So basically, anytime you do the change, it will be if anytime you do change to a files, and whatever the files are, it can be anything, right? So then it will be saved and kind of nicely organized in the versions. So Google Docs is a good example. Again, like I'm glad to hear that Microsoft is doing that as well. So that becomes widely adopted, even in daily life, because it started from computer science, obviously, and from programming, but it get to, which is nice to see, to kind of more general things like documents, for example, which is great. I think that's the right way to do. So in other words, these versions, right, like will help you. Oops, sorry. So will help you in tracking the changes in your data and the code and undo those changes as well. That's, I think, crucial, right? You can undo those changes, meaning that you can travel back in time and get whatever the version you need, right? So that's reassuring, because I think it's stressful to work with kind of thinking you're not allowed to make mistakes. No, you're allowed to make mistakes. Just set it up the system and travel back in time and redo things, undo things, and so on. So I think that's very kind of a good spirit. Oops. Okay. So why, again, just to kind of formalize it, why would you need version control? Help you to organize releases of the data analysis. And then I think one assumption it's fine to make, it's never perfect if you do it for the first time or like the first iteration of the analysis, right? So you will always add something or improve something. I think that's the case for those of you who are working with developing the software or heard anybody working with the development of the software. I mean, that's why you have versions, right? You have even Windows, I guess, right? You have different operating system and so on, or like the version of the software, right? It's never perfect. There is always a room to improve, but I think you want to do kind of a compromise in some sense. You still want to finish that to the best of your degree of your knowledge and release it so people can see it, but then keep improving that. That's why you need to organize that in the versions, right? Like public ones. So, and then releases. So you can release your data saying, okay, that's a release number 1. And then you say, okay, release number 2, we have improved things. Maybe we improved the data, we brought more data and so on. So it's like it's a live kind of like live working with the data, like in a transparent way. Yeah, then I think practically for you, you can revert back to older version. Sometimes you need that, as we discuss. And sometimes it's difficult to merge and keep track of each change, right? Obviously, because you need to pay attention to many files, but how about you have many files which are changing and so on, right? So automatically it's much better, much prefer more stable. And then I think ultimately also, if many people are working together, that's essential, right? You cannot survive, I guess, even working, I guess, on the paper, right? For example, if you work on the paper or any kind of writing, I think if many people are working, that's very hard to synchronize, right? But if everybody work on the Google Doc online, I think that's quite solves all the issues of the conflicts, right? If somebody is outdated, making the changes on outdated versions and merging them, or 2 people give comments at the same time, what you do? You need to merge them. That's like a nightmare too, right? So here, like version control solves all that, and then working in a team in an effective way. Okay. Oops. This one. Yeah. Okay. So just to kind of formalize it a little bit more. I think backup and restore, files are saved as they are edited, and you can restore file from any version, right? So everything is saved. Now you become an effective collaborator. You can synchronize the files with other members of your team, allow people to share files and stay up to date with the latest version, right? So it's effective collaboration. Short-term undo. Just if you feel like that you went the wrong direction, you can always kind of go to last known good. You know, like the moment you think you were right, so you can go there and try to change something. So track changes that as the file's updated, you can leave messages explaining why the change happened. I think that's very important, right? So like as you do the change, you know, like you can say, all right, like you can write some text. I'm doing here, I'm updating the plots and making them nicer, or I'm trying different versions of the plot, or I'm merging the data sets, like whatever the messages are. But you can say those messages. So when you look at your history, how things were happening, you can kind of see your logic. Oh, I did this here. And again, that helps you go back if you ever need, but also help you understand the analysis, how that was happening. Or I got a request, you know, like to do this. I'm trying this. I'm not sure if it will work. If it will work, you can make that message and then go back and say, okay, actually it did work, or maybe it did not. So I need to undo it, right? So it gives you a lot of flexibility. Sandboxing, you know, like, or insurance against yourself. So if you're making the big change, you can make temporary change in an isolated area, test and work out, and then push online, right? So you can work locally on your computer until you're kind of more or less happy with that change, and then push it online, right? Say, okay, that's kind of solid. I'm pretty sure, push it online. You know, so it gives you kind of this kind of milestones or like structure to your analysis, because analysis can be like many days or months, you know, so it's hard to keep track manually. It's sometimes overwhelming, but having the mix between working locally and pushing globally and seeing online already things to appear is very kind of encouraging usually. Okay. So, okay, let's talk about Git. So Git, I think, is the mostly widely used and popular modern version control software, right? So Git is the software, and GitHub is the kind of a service, right? So like which is based on the Git, but has more than just the Git. Okay, so but Git is fundamentally software for the version control. It's an open source project, you know, like so, and it was developed a while ago in 2005. So actually by the person who has also created Linux. So it's all about like, you know, like open, I guess, software and people committing kind of resources and time to develop open software to make the world better. I think that's kind of like very nice initiative. So, and then they get kind of like now quite popular and mainstream in science. So which is great, you know, like I think that's shows like that science is moving towards that direction, like open science and things like that. All right, so Git concepts, you know, like, so we'll talk about methods we use, you know, like by Git to keep track of your changes. And then we'll talk about the snapshots, which reflects the state of the files at the certain instant of time, you know, like what is now, you know, like you just make a picture kind of, and you say, what is now? Okay, so, and then, so repositories, so basically collection of all files, folders, and their history, all the snapshots, right? So that's important, which we didn't mention before, right? So it's not the files and the folders and the code and things like that, but also the history, how you were how you were doing the analysis, right? So that's important. I mean, sometimes we'll call repo if you'd like, or repository. I think repo is the shorter one version. Okay, so that's kind of the basic concepts. So what is GitHub, right? So we know what is Git now, right? So what is GitHub? So GitHub is the web-based Git version control repository hosting service. But again, it's more than that, right? A little bit more. But they give you kind of storage, for example, like limited one, sure. I'm not sure. I don't think there's a limit overall. At least I never hit that one. But I think there is a limit per file, right? So there is a challenge if you have individually, right, large files. So GitHub will be a place for you to store your repositories, right? If you have a folders with the analysis corresponding to a certain project, you can store them on the GitHub. And then it's quite abundant storage space. You can store your repositories and build a proper profile, which holds a great value. So what I mean, right? So actually it's quite common in hiring when you apply for a job, And I think that was the case even for some faculty position in the US, especially if you do bioinformatics. They ask, oh, can you give me the link to your Git? And that kind of speaks about yourself, right? Like, what is your history? Like what did you accomplish in terms of code development, open source software development, things like that, right? Tells quite a bit about person. So I think it's good to have it so that you say, okay, actually I'm doing reproducible data analysis and those are my projects, check it out. It's good to put on your CV, I guess. So that's I think it's a good idea. By default, the repositories are public, but it's everyone can, meaning that everyone can see your code and the data, right? But you can make them private as well. And you know, like now it's free, right? Before it was not free, but now it's free of charge. So you can do that. And again, I think the structure can be until you're kind of happy with the code and the results, and you can actually disclose them. But I think eventually it makes sense to disclose. Okay. Okay, so a little bit more, just to again formalize. So difference between the Git and the GitHub. So Git is the software, right? It's like a software tool. So GitHub is like more like a service. Git will be installed locally on your system, right, on your computer. In this case, on the Google Colab, you will install the Git. So we'll use it like software, you know, like similar like Unix command. You were using, let's say, ls, right? You remember what is ls? Or you were using cat and things like that. So that's similar. I mean, it's more complex, I guess, but it's kind of similar. It's like a tool for you. It's like a software you can use locally. In our case of the class, that will be Google Colab. And then GitHub, it's hosted on the web, right? It will be not on your laptop, but it will be hosted on the web. But the way to communicate with the GitHub will be Git, right? The software. Git is the command line tool. And then GitHub actually provides a graphical interface, right? So you can go on the GitHub repository and see what is there, right? Click the buttons and look to see. But I think in this class, we'll encourage you to use command line Git to communicate with the GitHub, because we think that's more effective. I mean, there is a possibility kind of to go on the web and kind of click the buttons and upload files and things like that. So I think it's fine, but if you learn command line, will be even better. Okay, so what is another thing about the Git is a tool to manage different versions of edits made to files, right? Like we are managing the versions, good. And GitHub is a space to upload copy of your Git repository, right? So it will be just your repository stored online. Git provides you the functionalities like version control and data management, right? So GitHub also provides you that. Just remember, Git is underneath of the GitHub, but provides you a couple of more its own features. Okay, so it's a little bit more than just the Git. Okay, any questions so far? So I think that's more or less what we need to know kind of in terms of kind of very generally speaking. Okay, so let's get to commands and we'll try to again minimize number of commands so that you can do things, but like not to overwhelm you with the commands. That's kind of the goal. Okay, so we'll call it essential, right? Git commands, and will be 1, 2, 3, 4, 5, 5. So how about we give you 5 commands? You'll try them and should be enough for you for now to get started. There is of course more than that, especially if you're working with others together, but that requires more, I guess, modules or more time. So we don't want to overwhelm you, rather give you essential commands. Okay, so let's read them and let's go one by one, yes. So we'll get Git Clone, Git Add, Git Commit, Git Push, and Git Pull. Actually, from reading, I would say, so some of them should make sense. So Git Add, something adding, right? Make commit, we'll talk about what is commit. Push, I guess this is the moment when you have the changes on your kind of laptop and you want to push them online, right? And Git Pull is exactly opposite. If your local computer is behind because you did changes on your working desktop, let's say, but online is up-to-date version, you want to pull it, right? You want to get the latest changes. So some of them will make sense, or they do make sense already from the names, right? But let's kind of formally go through them. Okay, so Git Clone will create a copy of an existing remote repository, right? Then Git Add will put the file into the repo for the first time, right? So you will begin tracking with the version control. So Git Commit will capture a snapshot of the project, right? So like you did some changes locally, you say, okay, I would like to add the files to the repo online, like let's say you have changed 2 files and you say, okay, I want to add those 2 files. And then when you do commit, you say, okay, I want to do snapshot. I want to take a photo of those changes and write some comment. I will say, okay, I have changed those 2 files because I did this additional analysis. That's like your comment. And then you say, okay, I'm ready to push that snapshot, right? That particular change I did online to the GitHub. And this is when you do Git push. Pushes any changes on your local repo to the repo on the GitHub. Okay, so that's it. Now you kind of synchronize to the extent you want it to be synchronized, whatever you have added. If you git add all the files which you ever was changed in your local repo, then things will be the same, right? But if you just change it 1 file locally and then push it there, but there are many other files which you didn't commit, so then it will be not synchronized perfectly, right? Because there will be some changes. So it depends on the purpose. I mean, very often, I would say to keep it simple, you just git add everything, right? You say git add star, actually. It will mean like every single file in this repo. Then you make things like perfectly synchronized, meaning the version locally will be exactly the same as the version online on the GitHub, right? So sometimes that makes more sense and kind of is easier to understand. And then Git Pull, right? So you went home, let's say you did this Git push at the work, you went home, and obviously your local repository at home is behind, right? Because you did some work at work, right? So then you say, okay, I want to Git pull. I want to take all the changes to my local. And then as a result, your local at home will be exactly the same as online and actually exactly the same at work. But when you start working here, the working one at work is behind. Okay, so as you see, it gives you version control, but it gives you some flexibility in terms of local computers, right, where you work, because essentially everything is online. That's kind of your thing you maintain and you care about. And let's say your computer broke. I am not wishing you this, obviously, but if that's the case, that's not a big deal, at least for this data, because everything is online, right? So it gives you some flexibility. All right, so I think that's all kind of in terms of commands. I think we'll not have more. Again, there is much more which not covering, but we are covering very much essentials. So basically the question, can we survive with these commands and do effective sharing? I would say yes. Like that's, I mean, again, unless you work in the teams, which will not cover in this module, but if you work by yourself, and then I think that's sufficient to do good data science and share effectively. Okay, so what you will do with TAs, and I just can briefly go through, you will create the account, right? So what you will do, you will create the account on the GitHub. It's free to do, so please do it. And you will open the account, you will go to the github.com, you will create your account, you will have some puzzle to verify, I guess, that you're the real person. Anyway, so some steps. Free plan, right? You will join free plan, you will pay nothing, so that's good. So, okay, so you will do those with TAs. Now, you will verify your email address, things like that, right? Again, you will work that through TAs, very straightforward. Okay, so now you go to your GitHub, right? Like you did all the steps, let's say, you go to your GitHub. So you can do a few things, I would say, like you want to create a repository. You say click here. So you will hit the new button in the upper right corner. We have it here, or just the text. Okay, and then, yeah, I think it's here. So, like that's you. That's like your account will be. In our case, that was data science UC. So, but then you say name of the repository. Like let's say you say test. You need to type here. I mean, it's not the type like type, but like type on your keyboard. So you need to type on your keyboard the name of your repository. Let's say it's test. Some descriptions. This is repository doing this. Fine, you can do that. Private or public. So if it's public or private, and then initialize this repository with Readme file. I strongly suggest to click here. Okay, so I think that's it, right? So you are ready to create your first repository. Okay, so this is how it will look like, your first GitHub repo, right? So this is how it looks like. So let's see what is here. So first of all, that's the name, right? Test, that's you. Data science, you see, that's you. It will be replaced by your login information, but then you have test. So the test is the name you decided on. Then that's what is inside, right? So you see, there is a one commit, right? Remember, when you run Git commit, that's like one snapshot you're pushing from local to online. So that will be reflecting number of times you did it. So far we did kind of once by creating that. I think we did initial commit. Actually, initial commit was because we created Readme file, right? That's our, and there is a comment here. It says initial commit. I mean, when we will be doing your commits from your local repository, and you will be saying things like, you know, like some sort of analysis, you will see your own text there. Which is kind of nice. So for each file on the online repo, you will actually see, you know, like some comments, how that file appeared there, which part of commit that file came from. Okay, so but now so far we only have one file, which is called readme.md, and then I think that's it, right? So and there is some, we can write it, we can click here and change that file, or we can do it through command line, both ways. But if you change it here online, you need to do Git Pull locally, right? Because you want to kind of take the changes from online. So Readme file, we'll talk a little bit more about that, but it's very important to kind of clearly describe the structure of your project, but also like provide some background, what is about, right? Okay, but so far, so good, right? So we got our first repo. Okay, so we can, I mean, theoretically, right, it's possible to do kind of all those three commands, you know, git add, git commit, and git push through GUI, graphical interface, no command line. Sure, you can do that. And then all you need to do, say, upload files here. Right, again, we want to try that I would like to encourage you to try to do it through command line, and I hope that will work, right? But so you know there is alternative also. So basically, by doing this button, upload files, you will do three things: git add, git commit, git push. Otherwise, you need that to do that from command line and type those three commands one by one. Okay, so for example, here you can see that we have added the folder, the directory notebooks, right? This is where we're going to store the notebooks. And we said upload notebooks. And you can see when it was done, you know, like relatively on time. And the comment, right? We said the comment upload notebook. So perhaps the situation was, right, we were working locally with this directory, and we created notebooks. And we said, okay, we want to kind of upload it online. So we said, okay, we're uploading the notebooks, and the notebooks went from the local repository where you created them to the GitHub. Okay, it actually allows you to effectively share notebooks. What I mean effectively, so when people go to your repo, they don't need to download notebooks, and they don't need to have special software. Remember, right? You cannot open notebook in the TXT file, but you need to have a software to open it, either being Google Colab, or you need to install Jupyter Notebook locally. So sometimes it's not available to people, right? So for those of like people curious about your, or like interested in your analysis, if they don't have coding skills, that's fine. Why? Because they can just click, right? They can, let's say you're collaborating with somebody and that person doesn't have any skills at all. That's fine. Or like software to open. So you can just send him the link, and he or she can open, click it here, and then see this kind of thing. And you see the figures actually, like, so it will visualize to the degree that in this notebook, you will see the commands, but also the figure. So let's say somebody doesn't understand the code. That's fine. Then they can look just at the figure, but perhaps appreciate that the code is also there, right? And you can briefly say what the code does. So they feel it's okay. That's like the entire analysis. Okay, so that's quite easy, right? It's quite easy to share. So we're talking about sharing your results. That makes it extremely easy, just because you don't assume anything about user, right? About somebody who will be checking your results. Like no assumptions, everything will be done on the web, just clicking on the notebook. Okay, I think that's nice. Okay, so let's kind of go to more practical stuff. So we'll talk about Git Clone, right? So just a reminder, Git Clone creates a copy of an existing remote repository. So the way we're gonna do will be always initializing the repo online, as we just did, and then we will clone it, right? We'll create a clone locally of that online repo. Okay, so that's how I mean, there's other ways you can kind of initiate from local, but I want to again minimize number of commands. So that will be not what we will be doing. We'll be always doing online, creating online, and then just clone. Okay.
Isn't this pooling? Or is it not the same?
No, when you do first time, it's similar to pooling, but Git clone it's actually, how should I say, it's for the first time. So when you have a repository online, but you don't have anything locally, right? That will be Git clone. But when you do have local repo and online repo, and you want to synchronize them, Git Pull, then you will be using Git Pull, right?
Yeah, makes sense. Thanks.
Cool. Okay, any other questions? Okay, so basically this is the moment when you created repository online and you are working on the new computer, or like you just for the first time, you want to create a local version of whatever is online. So you Git clone, you just create a clone, whatever is online. But you need to do it once. You do clone, then you just need to synchronize them. So that's you do for the first time only. Okay. Okay, so we'll run Git clone, right? So there are a few things. So what we'll do, we can click clone or download like this, but I think what we need to get the link, right? And I think you will talk, because there is some specifics about Google Colab, the way it's done. So I think TAs will kind of go into the specifics here, but essentially what you say, you git say in your Google Colab, you say Git clone, right? And then the link, right? So, and I think there is two ways to do it. It's either HTTPS link or like SSH link. So it depends how you configure out. So, but again, TAs will go through that and explain you that, right? But that's kind of the idea, because there is some specific, again, I mean, there's some specific of the Google Colab, the way you do GitHub there. Okay, so that, right? So running this command will create a local version of the repository, which is otherwise online, right? So you're ready to go. That's your first step. So you just need to do it once. If you're using new computer, sure, you need to do it again, Git clone there, right? But for the particular computer or laptop, you just do it once. Okay. So Git commit. So remember snapshot, like a picture, right? You did something on locally, you work on the laptop, let's say for 1 hour. You say, okay, I'm ready kind of to commit, to push my changes online, right? You say, okay, I did enough. I think it's correct. I'm quite confident, happy with analysis. I think it's time to kind of push it online. So you want to capture the snapshot. You want to take a picture of what happened. So, so snapshot will reflect the state of the files at the certain point of time. So at this time it will capture. And Git push, you know, like after it captures, it will just push that snapshot. It will push those changes. It will push those changes to the GitHub. So if the local changes are based on the most up-to-date version of the GitHub repo, this will go smoothly. So what that means, so you need, it's always a good idea if you're working on the multiple computers, right? So it's got good idea to always start with Git Pull. So you will make sure there is nothing new on the web comparable to the local. Then you're good to go. Because if not the case, then things will be hard, right? It will be some conflicts because your files locally will be outdated comparable to the online repo. Okay, so that's the first step you want to make sure, like Git Pull. I think it's next command, right? But after that, that should go smoothly. Okay, so push all modification to the GitHub, right? You will say git push, and then your username, your password, name of the repo, and all, right? So again, that's something you will work with TA. So I mean, just to make sure that works with the Google Collab. It's a little bit, usually it's a little bit simpler when you do locally, unless, and I mean, but again, since we're working the Google Collab, it will take a little bit, few steps extra, but again, TAs will be helping you with that. Okay. So let's see. So GitHub was updated, right? We did those commands. Now we have pushed what we did locally online. So we will say, okay, we want to look what is there, right? We go online and we should see the things, right? So we went after 1 hour, right? We pushed in 1 hour, we decided to check. That's why you see 1 hour here, and you see the new folder, notebooks, and this is what we have pushed. Okay, so now we have two kind of a folder and the Readme file online. Okay, Git Pull, right? So remember I mentioned that, but kind of to introduce it formally, obtains all updates to the repository on the GitHub and merge them with your local repository, right? So basically just like updates your local repository. So everything what is new online, it will kind of take it. But if there is any changes in your local repo, this will potentially create a merge conflict, right? So you think about how like the order of steps, right? So for example, again, you have, I mean, typically that will not happen much if you're working on the one laptop. Yeah, I would say it's very hard to create conflicts, right? Because there's only one source of updates to the online repo, but there is so probably no problem. But if you again switching the laptops, that might create some conflicts. So meaning that just think about the order. So for example, again, at work you have updated something. So online thing is like your laptop is behind, right? You came back home and you open the laptop, so it's behind, right? You know that. So, but even if you don't, just all the time before starting doing anything, just do Git Pull. And then perhaps it will tell you, oh, no new updates, you know, nothing to be updated. Okay, you're safe. You say, okay, that's a relief. Then you do the changes. Because the wrong way to do it will be open the laptop, not check that there is something new there, but start working and try to push. And then will be conflict because obviously will be some new files there. And in the worst case, you have changed those files here differently than was changed there, right? So think kind of like through, like, you know, like through the logic, like what is updated. But I think the good way to think to avoid anything, conflict, if you don't want to like, if you want a clear procedure, will be Git Pull before you do any changes locally all the time, you know, so that will avoid any kind of conflicts. And I think it's like in the worst case, again, we're not, you can resolve the conflicts, but we're not covering that again because it's complex. So what you can do, for example, if that happened to you, you can do the following. You can just remove local version or rename it some temporary file and do Git clone, do Git clone again. Okay, so start from scratch, kind of. So that's how you can manage the conflicts given the limited commands. We'll not go again into many commands because that might be overwhelming for many of you. Okay. So let's see. So yeah, so Git pull, right? Pull the changes made by others or by you. Okay. So how about Readme file, right? So that's a Readme file is actually written in Markdown language. So you, again, will not talk much. I mean, if you're curious about this Markdown language, I think it's interesting. You can read about that. So that's how you write kind of like the text, structured text with a very small number of commands. But I think you have, you know, like you can just write the text. And I think the only thing you need to know this hashtag. So that's called, I think, header1 size. And then if you put two of them, it will be large size, things like that. So it's quite, you know, like quite simple. But again, you don't need to know much about that. So so that's about Readme file, right? So and then we'll share, I think, with you some examples of Readme files. You can just, oops, Sometimes it's doing that. Oh, sorry about that. Okay. So yeah, sometimes, so like we'll share some README files with you, so you can just use as a template. But again, if you're curious, it's quite simple language. There's few commands you need to know. Okay. So so when if you want to edit that file online, right, and then when you click to save, actually it's a commit itself, right? Any change is the commit, right? So then if you do that online, right, on the website of the GitHub, it will ask you like what the commit changes, so you can describe like what did I do to the README file. Actually, I add link to the notebook per se, right? So you have added the link to the notebook. So you can describe it. So then you know. Now, but be careful, because now your online repository one step in front comparable to local one. So you need to Git Pull to update the README file, right? Remember, README file didn't know about that. Your local README file doesn't know what you're doing online. So you need to synchronize that. So you need to Git Pull. Okay. And then when you do pull the changes, actually it's quite gives you like this kind of. So if you run Git Pull command, this is how you do it in the Google Colab. So you will see what's going on, right? So what is nice, you can see what was the number of lines being added. You can see some idea how many things you have updated your local repository, right? So for example, you can see that you have taken the file. Okay. So in other words, you have taken what 3 lines, right? 3 new lines you got, but actually another 2 lines were removed. So you can kind of get the idea how severe the changes are, right? This way. And actually you can see some summary like this. 1 file changed, that's our README file actually. 1 file was changed. We got 3 insertions and 2 deletions, okay? When deletion, we mean the entire line. Okay, so you get some good summary, it gives you a good idea. So keep an eye on that, because things should, again, make sense to you. If you see hundreds, like maybe something suspicious, right? Maybe you're doing something wrong, but it should make sense. You kind of should anticipate what is the okay number. Okay, so check README. So README file. So you can actually open. I think it's, yeah, so after you change, I think that will be a good exercise we'll do with TA. So when you change the file online, check that it was actually updated locally, right? So what that means, the file locally, README file, should look exactly identical in the file online. So how to do that? You already know the command. That's why Unix is important. You know cat. You can say cat and the name of the file. So you should see the file. Looks correct, right? It looks exactly the same as online. Okay, everything is smooth and nice. Okay, so the way we'll be doing that is through Google Colab. As you did with Unix, you will add exclamation sign before the git or bash commands. I think that's one way to do it. I think another way is to put percentages. So I think it's I think they are more or less interchangeable. Okay. Google Drive can be used for permanent storage, and I think I think we have covered that, right? So Google storage is not persistent, right? So if you don't save things to the Google Drive, the things will be removed from Google Colab. Okay. I think, all right. So again, so that's something we can skip because we have actually covered that in the Unix session. So we will be skipping those slides. Let's see. Yeah, so the same. I think that's all. Okay. So interacting with the GitHub via Google Colab. So again, that's something you will be, when you will be cloning that, you will be looking through with TAs. Okay, interacting with the GitHub with Google Colab, the same. So I think those are commands you just like git add, git commit, and so on. So that's something you will practice, right, with TA. So that will be the commands you will be doing today. Git add, right? You just need to know for now what they mean, right? Git add, you're adding something to the snapshot. In this case, we say dot. So dot means all the files in the local repository. You can say dot star, add star, for example, also. So, and then you say git commit. That will be the command to commit. And you say -m message. You want to say some message. Upload notebooks and structure. Okay. Yeah, so you need to do some configuration. Again, that's something you will do with the TAs. And okay, so if you want to know more, kind of like to understand more why it's important version control with the GitHub and the Git, there is a good education paper in PLOS Computational Biology. Actually, not that recent one, so it was a while already. GitHub and Git people were using 2016, but it's a good one to give you kind of more perspective. But here I think we didn't go much, and I want TAs to do that like into like specifics of Google Colab. And they're a little bit different that you would normally do with your laptop. And again, the reason we use Google Colab just to provide you consistent environment across. Okay, so let's see, do we want to, any questions?
So do we have like some types of files that we can commit to GitHub, or like can we just add anything we want, like docs files, textual files, or just
Yeah, I think so. I mean, yeah, I think, you know, doc files will be interpreted actually as the TXT file. So you will not, I don't think there is a point. I mean, there is a good reason to commit good doc files because you cannot visualize them on the GitHub, right? Like if you upload doc files to the GitHub, I don't think you can open that. I mean, I never tried. You can try and let me know.
but could you use like the idea is like could you use GitHub like as a cloud service?
Yeah.
For anything?
Yeah, I think so. I mean, I think there's a limitation. Again, I didn't check recently, maybe they changed, but as far as I remember, there is no limitation on the total storage. However, there's a limitation per file, right? You cannot commit large files. I forgot what is quite big. It's like, you know, like typical files will be fine. Yeah, so you can use as the storage in some sense. Yeah. But I think like the way we see it, at least for this class, like we see it as only the files which is needed for the analysis, right? Like the way I want to at least teach it, that is only the files corresponding to the analysis. So, you know, I would say there is no need to upload doc files. I think doc, if you need some documentation, put that in the Readme file, right? So this is module 4, and then that's the second part of the module 4. So we would like to continue talking about the GitHub, but more so kind of in general lines, how we would share the data and code to ensure transparency and reproducibility. Let's see. Okay, and module 4, yeah. So I think the goal today is to understand different types of the data sets and how to share them and how we can share them. I think recognize different factors that impact scientific reproducibility. So there is such a thing as archival stability, meaning that do you store the data on the resources which will be for a while or forever around, right? So for example, not a great idea to share on your personal website because you can actually change your jobs, for example, and that website will disappear. So that's not a sustainable practice. I think the best practice is to store on centralized, public, and open source repositories and share open source software on those. And we'll talk a little bit about, just to give you kind of good background in terms of package managers and other things to solve installation issues. And then, yeah, so now you have the skills in the GitHub. So I think just like you need just a broader perspective on GitHub repositories, documentation, and README files, how to store the data. So we kind of like, we'll talk about that. All right, so that's what the learning objectives are for today. I mean, I think we talked that in the first day, but I just want to come back. So what are the barriers to do kind of computational or data-driven biomedical research, and especially reproducible and transparent one? There are a couple of barriers. I think lack of computational capacity. So if you're attending this class, you're in the right place to overcome that barrier and to learn and to get the skills. Yeah, so like I think bioinformatics analysis is kind of the same. So we will be learning that. Control access to the data sets and incomplete metadata. Those are the barriers. And people actually, by not doing reproducible and transparent science, they're creating those barriers, right? So if you're owning the data and you're not sharing complete metadata, actually you are the one creating those barriers for others to reuse your data. Okay, so I think again, like those are the slides we just, okay, so let me admit. So those are the slides I think you've seen before. So this is what we are doing right now, intense workshop or intense course to overcome the challenges. And I think that's important, that's possible. And then, you know, so this course is about this. All right, so so what about the barriers, right? Like metadata barriers. So like this is, we did a recent study asking, do people share the metadata, right? Like as you sequence, let's say, a particular disease, let's say you sequence, I don't know, sepsis, for example, right? Individuals with sepsis, and then the question, when you share the raw data, do you also share the phenotypes, right? For example, the phenotypes here on the y-axis. Do you share disease condition, age, organism, and so on, mortality, clinical severity, and things like that? So we have actually looked at that systematically across, I think, 4 different diseases, conditions across, I would say around like 30 or so, maybe 50 studies. So that comes to like 120,000 samples. So we have looked systematically at that. And we were interested, do people share the metadata, right? So as you can see, they quite nicely share the tissue type, let's say by the biological sex, more or less, organisms, and so on, but they quite not share ethnicity, mortality, clinical severity, right? So, and the difference is here, so you can see colors in the blue, I mean, dark blue and light blue. So those are, do people share in the publication? Meaning that they write the paper, just put the table, let's say, or just mention what is the ethnicity or mortality. But also that's actually not the best, because as you share the data on the repositories, like SRA or Geo, it would be also nice to share there. And that's actually, unfortunately, that is not required. Unfortunately, that's kind of up to you. And I think that's one of the reasons why people don't share the data, because it's not mandated. So what is advantage to share on the repositories? It's advantage that you can process it using code base, right? For example, you're studying sepsis retrospectively. So you have collected, or you have identified, let's say, 50 different studies. So it's very challenging to do it manually, right? To look through each paper. But how about you have 100 papers? Probably almost impossible, right? To look through each paper, to extract metadata and so on, because it's unstructured, right? It's just written in plain English. However, on the public repositories, there is a CSV file with the phenotype. So it's quite straightforward to get that metadata across any number of, let's say, thousands of studies, right? So that's extremely important. But you can see there's a huge gap. For example, the country. People do know the country, obviously, from individuals are from, but they don't say that in the repository, right? So, and then, so here we say the completeness of the metadata in the publication and in the public repositories. So you can see that sometimes some studies, so every dot is the study. So actually this is the box plot, by the way. We did it quite, so this is the project, ongoing project of the master student in the lab, Yuning. So he's not TAing, so he's on the interviews to get a PhD for PhD. So he's busy, but yeah, he did this plot. I think I'm pretty sure using some commands you guys are using. So that's, so you're quite well prepared to produce high quality figures. Yeah, I'm pretty sure he was using some version of Seaborn. So what is here? So we say that some studies really share 100% of metadata in the publication, but they never do, like never, not a single study share 100% of the metadata in the repository. So that's quite alarming. And some go quite low, around like 20% or so. So yeah, so that's, we published this paper in Genome Biology, and then we plan like a new publication, more comprehensive data. And then we hope to kind of raise the awareness about those issues, because I don't think many people think about that, but that's extremely important, because if you don't share mortality per se, and then you want retrospectively to study mortality, it kind of becomes useless, your raw data. Let's say you have a great omics data, like whole genome data, RNA-seq, whatever you have it. But if you don't share mortality, you cannot study mortality, right? Because you don't have that phenotype. And actually contacting the authors will rarely work. People, you know, like it's not scalable. It's quite hard to send 100 emails, and success rate is low. So I think that's one thing that I would like you to understand and kind of like understand why it's important. Okay, so yeah, so I think I've solved that. So just to kind of a couple of similar slides, right? So it's about data science, and then like reproducibility and transparency is the key of that. Okay, so types of the data, right? So we have, I would say, like kind of, I want to, I mean, like again, not going too much into details, but rather giving you kind of concepts, few concepts to be able, so you understand. So we have a raw data. So that's a data, the very raw from some machines, like some equipment, right? We have what usually we talk about the high throughput data, meaning there's a lot of data, right? This is what we mean, high throughput technology. And sequencing is one of the high throughput technologies, just because it produces a lot of throughput, a lot of reads in this case. So that can be genomics data, survey data. Sometimes it's not necessarily need to be genomics data, patient data, and so on. So that's all raw data, not processed. You didn't apply any cleaning, pandas, let's say, procedures or any statistical procedures on it. That's very raw. Now you do data processing, right? Data processing, in this case, we're using Google Colab, or you can use Jupyter Notebooks. You can also use R, Bash scripts, and other means to clean the data, to run some statistical analysis on it, and so on, right? To process the data. And then there is a data analysis software. So when we talk about bioinformatics, that's, let's say will be read alignment, which we will talk about in the last module, or HLA callers. You can try to call HLA type from your data. All that's actually can be, data analysis can be like softwares, could be something simpler, right? So let's say even pandas or some bash scripts as well when you do data analysis. Okay, so raw data, it can be public, as we discussed, or can be private. If it's public, that's great because you can reuse it. If it's private, unfortunately, often you can't, right? So you cannot access the data. It's a big trend to make the data public, which is a great trend. So I think there is a substantial fraction of the data which is public, but there is still some fraction which is private, and there is a big discussions about like what should be the model, right? Because it's actually interesting that people are choosing different models. So if you think about national project, like we mentioned Moldova Genome Project, which I hope will happen in the near future, but if you look around, and then there are obviously a lot of genome projects happening in the world, starting from UK Biobank, which is an enormous one, I think like hundreds of thousands of people and so on, like in the US, as well as, let's say, even neighboring country to Moldova, like Ukraine got its own project, I think due to some people I personally know, which were just like passionate about that. So they push the project. I think it was 100 samples, 100 individuals being collected to kind of make a first step in the genome project. But then it's interesting. And then there is a Qatar project, for example, in Middle East, or Saudi Arabia project. And then the reason I mentioned them just to contrast, to say that different parts of the world are kind of getting into this. But it's interesting to observe how people choose different models to share, right? For example, if you think actually about UK Biobank, it's kind of semi-restricted, meaning that you need to apply to get access, right? You need to apply and say, hey, I want to do this and this with this data. Can you give me the access? And probably they will if you're coming from university and things like that. But others, let's say like Qatar and Saudi Arabia, like no chance, right? They basically say, they don't say we don't share, but they make it extremely, I think intentionally, extremely challenging. So for example, I know about Qatar to get, which is quite nice data. I mean, they put some money in that. So to get access to the data, you need actually to come to Qatar, live for a while, for a couple of months, and you can access the data in the certain room. So you need to come physically to that room. So that's what they mean, we share, right? So, but it's probably not really sharing. And then actually there's some other examples, like for example, Ukraine did it all public. So all the data from Genome Project of Ukraine is publicly available, like completely. Like you can access as we speak, like right now. There is nothing is required. And I think it really depends on people. I think that like the people who are leading that, they just like they kind of share the same mind I do. So they like more open science and so on. So they just insisted on that. And I think maybe nobody kind of really I mean, people agree with them. So that's great, you know, but there is, as you can see, some variability how people share the data. And I believe there is no single answer because there is some concerns of sharing the data from which is I just recently heard actually that if you share, let's say, your data publicly, you can synthesize your DNA and put that DNA on the crime site, right? So there is a lot of concerns. I mean, maybe it's like, you know, like it sounds like very kind of crazy, fantastic, like, you know, some science fiction movies, but theoretically probably you can do that, but like legally there is a lot of concerns with DNA overall, right? So people are extremely careful. Not talking about the countries having some sentiments like Saudi Arabia and Qatar in terms of like sharing, they would rather oppose it. However, in reality, they still sequence, I think, externally sometimes. So anyway, so this is a very complicated issue. Okay, but what that means for you, like, I think you need to understand what's—
Sorry to interrupt. Are you talking about Derek Muller's short video on YouTube about how he showed how police in the US, well, I think the UK, I don't remember exactly, found the exact criminal, but the crime was just like, it was 20 or 30 years ago, but because they didn't have DNA banks and they could rule out, they actually could find the relatives of that criminal, and in the end, they could find the criminal.
Yeah, I mean, that's kind of different. Yeah, but it's also the same. Yeah, it's kind of the same thing of sharing the data. But it's kind of crazy that it's not only about you, right? You can be kind of very careful and never share your DNA, but that doesn't help. If your sister or, I mean, if your relatives, they do share DNA, so that's enough to find you. And they found exactly in Canada, actually in California, it was like, I forgot, Golden State murder, like a person was hiding for 40 years.
Yeah, exactly. Derek Muller speaks about this crime. It's a very short, like 20 minutes, but it was very, wow, sci-fi, but not sci-fi.
Yeah, no, that's kind of like, it's kind of, it's a very, and then who come up with that idea, obviously, like, brilliant idea, but it's quite simple from genetic perspective, right? Like to find, you know, like your DNA can match, like, okay, so from DNA from the crime sites, you can find the relatives of that person, like the murder, in the databases, and that's enough to kind of narrow down because you know something about the person. Like they say it's male, like this, you know, in this age, more or less. So they can like kind of, I think this is like what I read. I think they say, okay, we have few candidates, but then it was quite straightforward to sort it out, saying who exactly is that. And they say, okay, that should be male because of the nature of the crime, let's say, and should be this age more or less. And they check and so on, and they check the whole pedigree of that family, and they have found it. Yeah, I mean, it's like, that's another implication which nobody thought that will be the issue, you know, and that's a big concern of privacy. Because I think it's like, it's interesting discussion about privacy versus, you know, like say, like these kind of things, like finding the murders or like saving life of people and so on, right? There is some compromise, like, right? So for example, I think the best analogy I heard is that saying, for example, if we install the cameras, you know, like video recording in every single apartment, in every single room in the world of certain countries, we will solve the crime tomorrow. Like tomorrow, right? We'll know everybody what is doing and what is committing crimes, but do we want to do it, right? Will that compromise the privacy? Perhaps it will compromise. So the question, what is more important? Life of people to some degree, or certain people, or like privacy, right? And people choose privacy, saying that it's okay, certain number of people to die, right? And this is kind of very similar to COVID, right? Like in some sense. So there is some, it's not kind of black and white, right? We cannot say we care about every life. Yes, we do, but we can save more lives by compromising privacy. But perhaps we don't want that. We want to live our life private in some sense, at least. So that's a big debate, you know, like yes, that was correct thing to do, absolutely, to find this murder and punish him and put him in the jail or whatever. But that's why it's a very big concern, right? Like then you don't have some privacy in some degree. Due kind of indirectly, which nobody thought, because of your relatives, because of the high similarities of your DNA to DNA of relatives, right? So yeah, so it's not black and white. It's quite complicated topic, and you know. Okay. So what do we share? So if you think about RNA-seq data, for example, which we'll cover actually on Monday. So you have gene expression, meaning that you have reads, some sequences being attached or aligned to genes, that's your raw data. Then you have some pre-processing. And let's say you compare tumors versus normal, and you look at the expression, let's say, of the certain gene, right? So this is the expression of the certain gene, and you compare and say, do I see significant differences, right? So, and actually here, again, coming back to visualization, I hope you can appreciate now that's a good box plot. The reason is good because aesthetically, I think it looks okay. I think I found some in some publications, so it's not mine. So I think aesthetically it's fine, right? And then you have data points. Actually, they went beyond that, and you can see they put, I think manually, or like through some, how they call it, Illustrator, they put sample size, right? You can see here, sample size n equal to 159 and n equal to 115, right? So that's nice. And then they have clearly expression. So they just don't say, they not only say expression, as you can see, but then they also say the measurement, right? CPM, right? Count per million. So that's very important, right? So, and then they say it's a log scale. Yeah, it's not the log scale, but rather log of the value. And then they say tumor, normal. So I think it's like it has all the details you need here, and which is good, right? So, okay, so you would share, this is what you would summary data, right? So summary data, I would say the gene expressions will be summary data, right? So again, this is the raw data from the sequencing machine. Then you do some processing. Actually, the reason I put the fish here, there is a software called Selman. So let's say you run Selman software. And then after that, you got gene metrics, meaning that here you have, I think, yeah, so every column is the sample and every row is the gene, and every value is the gene expression. So it's a table which you can actually visualize at the heat map, which you already know, right? So I would say, I would call it, you can call it differently, but I'm calling this summary data, right? Meaning it's not raw data, but it's not the end data you will report, but it's like something you will be working with. So I think that's something actually you will be working on with RNA-seq. We'll give you some summary data like this, gene expression, so which you will work with. And you will find out the genes which are differentially expressed, meaning they're significantly differently expressed across cases controls. So this will be your RNA-seq assignment. Okay. Another question, how we would deal with extremely large files. So remember I said GitHub does not support extremely large file, but the raw data is generally large, gigabytes of size. So if you have raw data, if you have real data, meaning the data coming from people, from individuals, from animals, whatever, that you can share that on the SRA or Geo, right? Those repositories are interested in the real data, right? But however, if you do have some simulation data or maybe like the data, let's say non-genomic data, so they might not, SRA will not take it, so you need to store it somewhere. Okay, so GitHub has a file size limit of 100 megabytes, right? If you have file larger than that, you cannot upload it to GitHub. So, but you still want to share it, let's say, right? So what you do, you can use alternative resources like Figshare or Zenodo. And I think Figshare is free. I'm not sure about Zenodo. So you can share the files there. Okay, so again, if it's omics data, you have two choices: sequencing read archive at SRA or gene expression omnibus, Geo. So SRA is more for raw data and Geo is more for gene expression data. Okay, so I think you saw that before, so I can skip it. So Figshare. So we actually, personally, we are sharing the data on the Figshare in case we are not able to put it on the GitHub. So this is our example. So this is our paper published, I guess, 2 years ago, 1 year ago. So no, actually it was not 1 year ago, two, I guess 2 years already. So benchmarking of computational error correction methods for next generation sequencing, that's the name of the paper. And we said, okay, let's put the data sets, raw and true read, supporting the study, right? So since we did simulations, that's not real data, right? Just simulation data. So we simulated the DNA on computer, so we cannot pretend it's real data. So only choice for us was upload somewhere else, not on SRA, which we did. So we put things on Figshare. Okay, so we'll not cover how to do it again. That's beyond the scope of this course, but just want to give you kind of here larger perspective. Okay, so Zenodo. Okay, so we also did it. So then I don't think we paid, so I imagine it's free. So for another paper, we put actually it's a paper about metagenomics, about microbes. So we put the genomes of microbes there, right? So that's also another alternative. Okay, so in terms of when you do data processing, I think, right, we covered Jupyter Notebooks, Google Colab. This is what you're studying, and I hope you're more and more familiar with. And we also touch based on the script and the bash, and we'll do bash more for RNA-seq. And in general, you do a lot of bash for bioinformatics. So what we mean by software tools, that's something you will do next week. So for example, read alignment tools. When you're taking the reads from your genome and you're trying to match it or find the good placements of those DNA segments on somebody else's genome, which we refer as the reference, right? So I think we discussed that, but so as the Human Genome Project, we invested, as the community invested enormous amount of money to get one good reference of one particular individual. And we are matching your reads from the sequencing machine to that individual. So that's what we call read alignment. And we'll talk about that more in the last module. Okay, so here, coming back to these statements, right? We discussed that we talk about reproducibility and transparency. There are multiple reasons to do that, right? For yourself and for the community, but also it's a simple reason to comply with the requirements of the journal. So many journals, including, I think most of Nature family journals, require data availability statements and code availability statements. So that's something you should be able to write after this course. So for example, if you got the data, you need to upload that. So, or if you have used somebody else, if you have used the data, you should mention that, right? For example, we were using RNA-seq data, which was part of the Genome Tissue Expression Consortium, and we mentioned that, right? And then another data, which is BCR, B-cell receptor data, is this, right? So we describe every data set we use and then and then the link. But we also describe all the data required to produce the figures and analysis performed in this paper is freely available on the GitHub. That's why we covered GitHub, right? Because I think it's important to be able to create the GitHub and share your results and put it in this format, right? So you can claim that every figure I did in this report of the paper, go back to my GitHub and you will be able to reproduce each of that, right? So that's your ultimate goal. And we actually very specific, and I think this is what Nature communication requires, that we are very, very specific about, which figures can be reproduced. Because some figures are obviously schematics, right? There is no data behind them, but many figures are having data behind them. So we say explicitly which can be reproduced. And the same for the code availability. And by code, we mean as simple as like a couple of lines of your code to produce the box plot. So that's important. So I would say it's a good practice to share that. And we do, and you can see how we are describing that, right? So we say, okay, all the code, this is the software in this case, right? First line, we just developed the software. That's less relevant for you, but I think this line is relevant. All code required to produce the figures and analysis performed in this paper is freely available at, right? Okay, so that's something you will be able to do, right? So you know how to do pandas, you know how to do Seaborn, and now you know how to do GitHub. So that's the statements you can write. Okay, so then it's a good practice to mention software tools, to say, like which software tools were used and for what, and things like that, right? So that also adds up to reproducibility. Why share your data publicly? Because it's essential for reproducibility. So meaning others can reproduce your results. And then it's required by many journals. Okay, so what are the factors which impact reproducibility? Open code of the analysis, archival stability. Are you using centralized repository? Are you providing the commutation, Readme file? sharing data, both raw and the summary data. So let's see. I think open code of the analysis, that's clear, right? You need the code to reproduce plots. Archival stability means that do you share on the GitHub, for example, right? Then you're fine. GitHub will not disappear. But if you share on the website, your personal website, let's say, however, you decided to switch jobs or close that website, or you're no longer paying for that, any reasons, right? That will disappear. So it's not archivally stable, right? It will disappear. So you will lose, community will lose access to your data and results. Centralized repository is why it's important, because people can search, right? They can go, let's say, on SRA and look through all the data sets, because they will assume everything is there rather than looking across the web, which might be challenging. Okay, sharing data, I think both raw and the summary data needs to be shared. And documentation or Readme files, just essential so others can reproduce the results you did. And then kind of understand how the repository is organized. Okay, so let's see. Time is now. So I think the TAs are here. So what do we mean by archival stability? By archival stability, we mean kind of like preserving the particular recordings or particular analysis results and so on, and can be readable over the time, right? And then that's a big problem. Like before, when we got the books, I guess, right, you just need to maintain the book, but as soon as like the library is not burned or like destroyed, the books will be there. And then as we switch to web and online, that's extremely tricky, right? Like how we preserve information on the web. That's a very open question in general. Some people do research in that. So I think personal academic websites are less stable. GitHub and Zenodo and others are more stable. I mean, it's an open question. Will GitHub be forever? Or like, let's say it will disappear. We don't know that. But for now, we can assume that GitHub is a good resource to maintain your results or like analysis to be readable across many, many years. Okay, so package managers, just wanted to kind of touch base on that. So the package managers, so basically when you do, which you probably didn't experience yet, but as you go with the bioinformatics research and biomedical research in general, you will notice that it is extremely hard to install tools. Like it's extremely hard to install bioinformatics tools. And for various reasons. So one reason is that the people who develop the tools don't necessarily have all the expertise to do software development. That's one reason. Two, people are rushed. So usually many software are developed by graduate students, and that's challenging because they need to finish the PhD in time. But also, I don't think it's, they need to do multiple things. And then it's not that appreciated in the bioinformatics or like in biomedical community. Like, for example, if you do a PhD and you just develop a tool, like, and you kind of did everything, all like, let's say 5 years, like we do, like your PhDs in US, like you do 5 years tool development, I would say that's a very risky move in terms of your career, because people might think you did very little, even though you were working hard. So people do compromises. They do some decent job developing software, sometimes poor jobs, and they push publications and they do another project. So there is a lacking component of good software engineering practices in academia. And then another reason, it's very hard to obtain the funding. For example, nobody can get the funding just to develop the tool. You should hide it under the hood and say, hey, I want to study, let's say, risk of cancer across certain population, but for that, I need to develop a bioinformatics tool, right? So there is multiple complex reasons for that. So anyway, so I think there are several solutions for that. So there is Anaconda, CRAN, and Bioconductor. Those are package managers which make installation easier. I think you might touch, we'll see if we will have time to talk about Bioconductor and CRAN when we do talk about RNA-seq. But just to let you know that there is, as you go with installation of the tools, those will be the things useful to install the tools and work with software. So yeah, centralized repositories, extremely important because we want all the DNA data to be kind of stored, or genomics data to be stored in a kind of centralized location. So personally, I can come and say, I really want all the data sets from these phenotypes, and I will be easily getting them. So I don't need to search the entire web. Not talking about that's very expensive to store. So there's a big investment of money in maintaining those terabytes and terabytes of data on SRA and Geo, right? Okay, documentation, extremely important. Okay, so let's see. So documentation is extremely important. And because, yeah, so we want to describe the software, and it's a good kind of tone at the practice to describe the software you develop, but actually the analysis you do. I strongly believe you need to provide documentation with the analysis you do. I mean, why? Why do you want to write documentation? I think the general reason is you will be using your code in 6 months. I doubt you will remember much, right? So it's quite nice. Do it for yourself, but then you will also do for others. Or if you want other people to kind of look at your code and like understand what you did, that's important. And then sometimes, you know, if you do the project where you expect others to contribute to your project, then it's absolutely the must, because otherwise they cannot kind of understand what you did. I think it encourages open science in the end, you know, like, and then sharing everything, being transparent, reproducible, and clear what you did. And ultimately, yeah, it enables reproducibility and transparency. Okay, so Readme file. So that's one example of the Readme file we do. So we put it in the root directory, meaning in the very kind of main directory of the GitHub. Actually, it's created as we saw. It's created if we click that. If we check that we want to have a Readme file, that will be created for us. And then I think it provides information about the repository content. So if you want to see an example, you just need to click here on this link. And this is our own one. So this we follow more or less. There is no kind of rules in some sense. There is no kind of a template that everybody is using. So we defined our own template and we try to follow that across all the projects we do in the lab. So to be precisely the same and consistent, right? At least within the laboratory. We cannot enforce the entire university to do the same, but at least for our lab, we have all the control. So this is what we say. We say how to cite the study, reproducibility, reproducing results. And actually we did the typo here, I just noticed. Tools, data, notebooks, and the figures, license, and the contact, right? So this is our standard things we put there. And, you know, like we say how to cite the study. Actually, it's also not updated. We need to say that the paper was actually published. So we need to update this. But we say how we would cite it, how would you reproduce the results, what we did, whom to contact, you know, like all the information people need to know. And then you can notice that we put notebooks and the figures, right? We put the notebooks, which needs to be run to produce the figures, and we put some data here and some tools we have used. So we try to be as comprehensive as we can. I think those elements are important. You know, like titles and internal titles. Like you feel free to follow our structure if you're interested. If you're not, come up with your own one. I think you want to introduce the project. You want to say, what is the aim? Assume people don't know about your project. Say, hey, I'm trying to do this, using this data. Technologies, you want to say how raw data was produced, perhaps. That's, I think, very useful. And what you run and so on. You know, like you can add table of content, illustration, examples, status, you know, like is it the work in progress? Is it like complete work? How to cite it if so, and other information. So, you know, like, I mean, again, you can follow what we did, or you can come up with your own structure. Okay, so that's an example of the Readme file. You know, like open it, look at that, and like see if you like that. And actually, you know, like you can even try to reproduce it and let us know if you're able to. Okay, so I think we follow very strict rule again, personally in the lab, like to organize your repositories. And actually it's beneficial for yourself, you know, like it's quite nice to open every single repository in our lab and see and be able to find the files quickly. I don't know about you, but I cannot, I mean, I have hard time remembering like how I did things many months ago, you know, like so, and then it's very, when you open repositories, you know where to go, where the data is and where other things are. But if you keep the same structure, you will always know where to go. You say, oh, I know, the code is here, data is here, notebooks are here, and so on. So it's very beneficial. It's even for yourself. Okay, so this is, I think we showed this to you before, but just to kind of remind you, this is the structure, right? So we have some summary data. So we have some CSV files because we assume the summary data is CSV. And then we have notebook. We have some notebooks. So we have some figures. We also save the figures, which are high quality figures, which will probably go to publication or otherwise go to report or anything like this. And well, we also often in publishing process, we also combine, probably you saw that, combine the figures into multi-panel figure, right? You have a figure composed of many, many different figures. So that's what we call multi-panel figure. So that's our typical structure, right? And you can see the arrows, for example, to this notebook, right? Figure 1 notebook takes 2 files and produce 2 figures, right? And those 2 figures are combined in 1 figure. So the AI is the Illustrator, right? We use Illustrator, Adobe Illustrator software to combine the figures. So the same here. For example, figure 2 will take 3 files and will produce 3 figures, right? So there is some structure behind, right? So if you do this, it will be very clear for everybody, like what are the files there, what are the notebooks there, and what you're trying to do, and so on. And then you'll notice we have a major README file, but we also sometimes add README files for each directory, just to say if there is anything specific we would like others to know, or actually for us, for later version of ourselves, to let to warn or like to give something to say something important. Okay, so yeah, so this is example. You can see here figures multi-panel, notebooks, scripts. Sometimes we also need scripts, summary data, and then general README file. So this is how it will look like. Okay, so summary data, again, that will be generally CSV files, because I think more or less all the summary data can be presented CSV file. We just keep one format just to keep it simple. So those are CSV files here, right? Oops. So this is notebooks, right? So you can call them by figures. You know, you can say figure 1 notebooks, or maybe call it something else. In this case, we call it by data set. We have D1, meaning data set 1, underscore whole genome sequencing, and data set 1, whole genome sequencing, and so on. Okay, so those are the notebooks, right? And then they will take CSV files as the input and will produce the figures as the output. So this is how it will look like, right? Remember, I said that on the GitHub, you can actually visualize the GitHub notebook, which is very important. So you don't need special software to look at the analysis, which is crucial because it's, again, you're targeting quite a broad audience, not only the ones who know how to open notebooks, but rather everybody. Okay, so very important thing. When you're reading the data, you should use the relative path. Never use absolute path. Why? Because your absolute path will be different from somebody else, right? So then will be non-reproducible. But you can clearly assume that the CSV file is located 1 level up, right? That's why we put 2 dots. And the directory is summary data, and that's the file, right? So if you do relative path, that should be fine. That will be reproducible, right? That's why we covered Unix, right? So that's why, I mean, kind of for you to understand how to write the path. Okay. So actually, and then saving, the same with saving. When you're saving, don't use absolute path, always use relative path. And then you can save to PNG and PDF. We save both just in case. You can always do PDF, or you can only do PDF, or you can only do PNG. But what is nice, again, about Jupyter and the GitHub, you can see the figures inside, right? As you collect, you can really check the analysis. Write the comments, you know, like I think it's a good practice. Look here, heat map depicting the gain across various coverage settings. Each row corresponds to the error correction tool, and each column corresponds to data sets with the given coverage. So I think it's a good practice. Like really explain, don't give interpretation. I think this is what your paper or report is for, but you want clearly to describe what is the figure, you know, like how the figure was selected. For example, it's not only about every tool, but we actually selected whatever k-mer size select. So we give enough details to people appreciate and understand the figure, right? What is exactly this figure about? All right. I think you can do a lot of subfolders. Sometimes you could really have a lot of files. For example, for figures, we got like, I don't know, 50 figures, too much, right? To put it in one directory, we say, okay, let's split it by subfolder. So let's create subfolder, which will be D1 whole genome data E. coli, for example, and we put all the figures there inside and so on. That's a good idea if you have a lot of figures and files. Actually, just the images can be also visualized. I'm not sure about PDF, but that's why we put PNG as well, I think. So PNG can be viewed kind of on the GitHub. I'm not sure about PDF. Probably you need to download them. Actually, you can try and see. Okay, so, but I think it's nice to have both versions. If people need PNG, they can take PNG. If they need PDF, they can take PDF. All right. Multi-panel figure, again, that's something very specific to publishing. Like actually it's specific to certain journals. Not all the journals do that, but many do, like Nature Family journals. On others, it's very common practice, because I think there is a very simple reason for that. In the journal, you're allowed to have 3 figures, for example, right? But you want to increase the amount of information you're kind of saying, you're like delivering. So that's why you put multiple box plot in the one figure and call it one figure, right? So if that's the case, so we create AI file which combines all the figures, like together in the Illustrator, Adobe Illustrator. So and then we also save as a PNG, so it's a final product as well, because not everybody will have Adobe, Adobe Illustrator. Sorry, I keep forgetting the name of the software. Okay, but there is also another alternative, right? There is Inkscape. I think it's free. There is a couple of other free alternatives because you need to pay for Illustrator. Okay, I think that's it. So I think we're on time. Any questions? So I think that was more general information for you, kind of to understand how things are done. I mean, hopefully we'll be doing that. That's kind of not strictly required by this course, but like as you do your individual project, we will ask you to create the GitHub, to organize your data, and to write some sort of Readme file. Maybe not that extensively, but I really want to provide state of the art, what we believe the state of the art. Sharing the results of the analysis. And I think in general, sharing the results of analysis is as important as the analysis itself. Okay, so any kind of questions so far?
I have one. Do you use one repository for each project, or
yes,
many projects are included in one repository?
One repository for each project. Just like, that's much simpler, avoids the confusion. But you can create your organization, for example, actually under yourself. You will have a GitHub account, and you will have multiple repositories. Yeah, which are actually even the name. Like it makes sense to call it like project, whatever the particular project, and keep only the files related to that project in that repository. Okay, good question.
Thanks.
So, sure. Any other questions?
And the notebooks, do you use mainly to show how you produce the figures, or
actually not only the figures, also processing steps. Like if you clean the data or you remove some data. I mean, let's say you have a data, but you need to remove certain outliers. I think it's nice to show that as well, so people can see that how you clean the data.
But if the process of the analysis is very long and
yeah, that's fine. Just share the long
it's just so, and you do the analysis in notebooks.
Yeah,
or
I mean,
just in your laboratory.
Yeah, we do notebooks for not the bioinformatics. I mean, okay, so if the analysis is non-computational intensive, like you don't need high performance computing or supercomputer, but it's rather you can run on your laptop or things like that, or Google Colab. Yes, we do that all in notebooks, but we can split. For example, it can be separate notebook saying cleaning the data or removing outliers if it's too long, right? If you're talking about extremely long notebooks, you can split it and have a notebook. Let's say you take raw data, you have, I don't know, removing outliers, done. Then produce another CSV file and then goes to another notebook, which does something, another cleaning. But yeah, I mean, we do that stuff in the notebooks.
Yes, thank you.
Sure. Any other questions? Okay, great. So I think, again, that's something you will be using when you will be sharing individual projects, like towards the end of April, or if you want to do it early, you can. But that's something you would need to kind of understand. We'll give you obviously the requirements, very strict or clear requirements, how to share individual project. But like I wanted you to also understand how it's done in kind of in real projects as well. So you have good understanding. Okay, so I think that's all for lecture today.